Hello, in this video we are going to be looking at modeling linear and exponential scenarios, and we want to be paying attention to what might be the differences between those scenarios. So we'll start by reading some information about some COVID data that is from spring of 2021. This is where we saw vaccinations increasing and we saw a huge drop in COVID cases. So on April 17, 2021 is when we had the peak of the spring wave with a 7-day average of 4,947 new cases in Pennsylvania. Over the next 5 weeks, the 7-day average decreased by about 749 new cases per week. And we're to use this to create an approximation of the average number of cases per week. So in order to do this, I want to really think about what does the word decreased mean? And so as I think about that word, to me, that is a subtraction word. So if something's going to decrease, it's going to go down in value, and mathematically, that is subtraction. So what I'm going to do to complete this table of data, I'm going to take the 4947, and I am going to subtract the 749. And so thanks to my calculator, I get 4198 as the number of new cases a week later. And then it said it did this each week. So I'm going to, again, take the 4198, my answer, and subtract 749. And again, with the help of my calculator, I get down to 3,449 average new cases per week or per day a week later. And I continue in this pattern. So I take the 3,449 minus the 749 and I get 2,700. I subtract again. And I get 1,951. And I subtract one more time. And I get 1,202. So then it asks me to create a line graph of this information. So I do have to do a little bit of approximating, but these numbers are pretty close. So the first date is April 17th, and the cases are very near 5,000, so I'll make that my first dot. By April 24th, I am much closer to 4,000, but a little above, almost 200 above. So I'll approximate that here. By May 1st, I'm down to about 3,500. So I'm going to estimate the middle of that box. By April 8th, 2,700. So that's a little below 3,000. By May 15, I'm at 1,951, so really close to 2,000, just slightly under that. And by May 22nd, I'm down at 1,200, so a little above the 1,000 mark. So these are my best estimates. I'm really not great at drawing lines online here, but I want to attempt to go through my dots. So you're seeing a little wavering, but it really appears that if I could draw a straight line, they would be on a straight line. And so what I did is I went out and used technology. And so I put in these numbers that we calculated and had Excel draw the graph for me. And you can see that Excel drew a perfectly straight line. And so that is that first scenario. Our second scenario continues with the COVID data, but as often is the case, we see that it doesn't drop as significantly after a little bit. They start to see a slow in the decline. And so we can't drop by 749 cases for very long, or we go to a negative number. So from May to June, we had cases drop by about 30% each week. So they're still dropping, and as I think mathematically, dropping is that idea of subtraction. But they don't tell me how many to subtract, they tell me the percentage to subtract. So I'm going to think through this with the idea that I started at 100% and I'm going to drop by 30%. So I'm going to subtract out 30%. And so that means I'm going to have 70% that remains after the drop. Now, if I want to do math with a percentage, I either need to change it to a decimal or I need to work in a proportion. So my understanding is that from May 22nd to May 29, this will drop, it will go down by 30%. And so that means that May 29 would have 70% remaining. So percent goes over 100, so 70 over 100 is equal to x, the part that remains, out of the 1202. And we have many times this semester solved these, so I solved by cross products, so 70 times 1,202, and then divided by 100. And because it is people, I did round to a whole number, so I had 841 cases. And then I repeated the process. So a week later, this would have again dropped by 30%. So I would have 70% remaining, so 70 out of 100 is x out of, this time, 841. And so again, solved by cross product, rounded off to a whole number, so I had 589. And I've repeated. So understanding the exact same process every time, so 70 over 100 equals x over, this time, 589. And I solved that out, and I had 412. And one more time, 70 over 100 is x over 412. And I solved that out, and I had 289. So I will attempt to plot these values on the graph and take a look at this graph as well. So at the beginning, we were very close to 1,200. Then we went down to 841, so just a little above 800. Then we went down to 589, which is just a tick below 600. Then we dropped down to 412, so a tick above 400, and finally to 289, so about right in the middle here. Again, I want to try to make a line or curve through these. This time, as I connect my points, and again, I'm attempting to make a smooth motion here. It definitely feels like there is a leveling off, and many times we have seen that leveling off as we ourselves may have watched the COVID numbers. So my curve, not perfectly smooth, but again, I went out to technology, asked that to do it for me. Here I have the numbers with all the decimals, and we rounded these all off to whole numbers, but this shows you the exact values. And we do see that this starts to curve or to flatten. The drop-off is not nearly as steep as it once was. And so from these two scenarios, we want to make some observations and begin to tell them apart. So we are to write observations of how the data changed. So it changed, it went down by the same amount. Every single time. So every single time there, I subtracted, and I subtracted the exact same amount, and that gave me the new value. And so mathematically, we describe this as having a constant rate. And so that's where mathematically, when it goes down by 749 cases per week, so that constant rate in our example would have been negative for the down by 749, and this would be cases per week. And so anytime we have that per and a time frame that's described as a rate, but this rate remained constant, it always went down by the same number. In question 2, we saw that it did not drop by the same amount. So instead, it dropped by the same percentage. And so when we have that drop by the same percentage at the beginning, when the total was pretty big, it dropped by a bigger amount than later on. So it did not drop by the same amount. So we're to write observations about the shape of the graph. So the first graph turned out to be a straight line, and we saw that best with the technology. And the second graph ended up having some curve to it. So naming wise, when we have the straight line, we call it linear. When we have the curve with the constant percent, because there's lots of curves out there, but specifically the curve with the constant percent, we call those exponential. And we have two formulas, one for linear and one for exponential. And we'll get into the details on those formulas in our next video.